Now we're going to do a few practice problems here with linearization. So the first thing we're going to want to do is graph our initial data. So we see here we have our independent and our dependent data. So we're going to make a scale on our graph and then go ahead and graph it. So what I'm probably going to do for my x scale is I'm going to say each block or every 2 blocks is 1. And for my y scale, I'm actually going to use the same scale, that every 2 blocks is 1. So I'm not necessarily going to fill in every single tick mark, but just a few of them so I know what it is. And now I'm going to go ahead and graph this data. Once I have my data, I can go ahead and draw my best fit line. It's going to look something like that. We see that that's clearly not linear. What this looks like is a square root graph. So what we're going to do is we're going to change our axes, and instead of graphing x on the x-axis, we're actually going to graph the square root of x. So we see that this graph takes the form y equals k, some constant, times the square root of x. That's the current form. So the way that we linearize it, the way that we turn this into a linear graph is we basically anticipate what that function is on the x-axis, right? We make that x-axis be the square root of x. And what that does is it makes this graph then be in the form y equals some constant times whatever is on the x-axis. And that is the graph of a line there, okay? Because it's simply some constant, which we typically call the slope, times whatever is on the x-axis. So that's how we're going to go ahead and linearize it. If it's y equals k times the square root of x, we're going to put the square root of x on the x-axis. If it was y equals k times x squared, we'd put x squared on the x-axis, all right? So whatever that function is, you're going to put that on the x-axis, and then what is normally a curve or nonlinear graph will become a linear graph. So the first thing I'm going to do is I'm going to redo my data. So my new data now is going to be the square root of x and y, and so my y values are going to stay the same. My x values, though, I'm going to take the square root of all my initial x values. So I'm going to go ahead and write out my new data table. So I see here that my x values are just the square root of those initial ones, and my y values have stayed the same. Okay, so I'm going to once again make my scale. On the y-axis, I think every 1 being 1 is fine again. Nothing's changed there. On the x-axis, though, I noticed that they're not quite as spread out. Before it went all the way to 10, now it only goes to 3. So I'm actually going to say that every 2 is 0.5. Okay, and we're doing that because we don't want to have a graph that's all scrunched into this small area here. We want to spread our graph out. So that's why I'm going to go ahead and do that. And now I'm going to go ahead here and plot the points that I have. So I'll do that, and then I'll draw my best fit line. So now I have all my points plotted, and I'm going to go ahead and draw my best fit line here. Going through all the points, so something like that. Slide it down just a tad. Alright, so now I have my best fit line. The only thing that remains now is I want to go ahead and find my slope. And I want to find my y-intercept. So in order to find that slope, I'm going to pick some points here. Don't necessarily pick points that are on your data table here. What you want to look at is you want to look at your line. You want to look at points that are actually on your graph itself. Okay. If they happen to be data points, that's fine, but don't necessarily assume that one of these points lies directly on your line. So I'm going to pick this point here, which looks like it is 0.75 and 1.25. And I'm also going to pick this point here. Those are decently spread out. So we do want to pick points that are relatively far away from each other. And that point there is going to be 2.25, 4. So I can go ahead and get my slope, the change in y over the change in x. So I find here, using those points, that my slope ends up being 1.83. And my y-intercept, I'm just reading that graph and seeing where it intersects, and it looks like it's about 0. Maybe not exactly, but close enough to 0 that we can call it 0. We have another linearization practice here, so same thing. I'm going to go ahead and make my scale. On the x-axis, I'm going to say that each block is 1. On the y, we're going from 0 all the way up to 20. All right, so I'll say maybe that each of these smaller blocks here is actually 2. That should give me enough room to do that scale. Now that I have that scale set, I'm going to go ahead and start plotting some points. And we should very quickly be able to see that this graph drops off very quickly. It has a shape that looks something like that. That shape where x is increasing but y is decreasing is indicative of an inverse function here, okay, which takes the form y is equal to k, some constant, times 1 over x. So this 1 over x, that's what we're going to plot now on our x-axis. So the first thing to do is switch our data around and plot 1 over x rather than x. So now I've rearranged my data here. I now have 1 over x as my dependent variable, or what's going to be on the x-axis, and just y on the y-axis. Once again, I'm going to set up my scale and go from there. So I'm going to maintain that same scale on the y-axis, with each block being 2. On the x, I'm going to say every 2 blocks is 0.1 here. Simply because my x values are just ranging from 0.1 all the way up to 1. So again, we want to spread that graph out as much as we can. Alright, and so now we have a graph here, and this might be a little bit tricky to see. This does end up happening when we have inverses, where we have pretty big gaps between our points out here, and then they're really bunched up here. But if we quick try and draw a line here, I think you're going to see that this is very clearly not a linear graph. If we draw that line there, it severely misses that point. If we draw it straight like that, it misses those other points. So a line is not going to be our proper fit here. If you look closely, you kind of have some sort of a curvature going up like that. And that's what our graph is going to be. It's going to be a quadratic. So that doesn't mean that we did anything wrong. We were right to do that inverse. That was the correct move. However, it does mean that we actually now need to square our x values. So it's not, we originally thought it was y equals k times 1 over x. It's actually y equals k times 1 over x squared. Okay? And so we're going to need to change our x data around once again. So as you can see, our data is obviously getting very, very bunched together here. And unfortunately, that's just the nature of this type of graph, all right? And we're just going to have to do the best we can. In the future, we'll usually be doing these on Excel, so it'll make things a little bit easier to deal with those really, really small, close together numbers. I'm going to maintain the same scale on my x, same scale on my y, and then I'm going to go ahead and graph these points here. Just a quick note though, before we start graphing, as much as you might want to do that thing where you skip points, okay, you have to maintain a constant scale on your x and your y. Otherwise, you're not going to be able to properly see the shape, all right, and your graph just isn't going to look correct. So that's what we end up getting here for our graph. Like I said, the points are even more spread out now, okay? But we can see if we do add a line here, that is a much better linear fit. Those points clearly fall along that line. So let's go ahead and get the slope of that line. So I'm going to take this point here, which is going to be 0.2 and 4. And then I'm going to look for another point kind of near the end here. This might not be a perfect intersection, but this point 0.7 and 14 looks pretty good. So we'll go ahead and find the slope here, and then I'm going to look for my y-intercept too. So my slope, as always, is my change in y over my change in x, so 14 minus 4, or 0.7 minus 2, and that ends up giving me a slope here of 20. And my y-intercept I can get from just reading my graph, and that's going to be 0 once again. So there you have it. That one's definitely a little bit trickier because of the double linearization. Okay, we linearized it once, it still wasn't linear, so we linearized it again. That will happen on occasion. And the points get a little bit bunched up, but this one definitely looks like a much better fit. Like I said, it's going to be a lot easier when we're just doing this with a computer program such as Excel, but I think it's important to learn it by hand as well. All right, moving on to the last part here, and that is kind of working backwards a little bit. One of the things we want to be able to do with linearization is use it to verify given relationships. So if we know what the relationship should be between two things, we can take some data and use this technique of linearization to verify that that relationship is correct, that mathematical relationship is correct. And a lot of times too, we can use the slope, use the y-intercept to get some useful data on certain constants in our problem. So the way we're going to do things like that is we're going to take our initial equation, take our initial relationship, solve for the dependent variable, what we go on the y-axis, and then pull out any constants and kind of match it up with our equation for a line, which you remember is y equals mx plus b. So let's work through this first example here, and I think it will make a little bit more sense. So for this first example, we're starting with the equation for the volume of a cylinder, pi r squared h. And what we're told is we are measuring the volume, okay, while the radius changes. So the radius is going to be our independent variable here. The independent variable is the thing that you physically have control over changing. The dependent variable is usually the other variable, the thing that you're measuring, but the thing that you are not directly controlling. So in this case, that would be the volume. Height here, by the way, is going to be a constant. Okay, that's not changing. So we first want to isolate our dependent variable. Turns out our equation already does do that. And then we're going to pull out any constants. So the constants that we have are pi and h. So I'm just going to rearrange this equation so that all the constants are out front. Pi h, and then I have my independent variable r squared. So we're going to match this up to y equals mx plus b, and that's going to tell us what goes on each axis. So on the y-axis, we're going to have volume, right, because that volume matches up with y. On the x-axis, we're going to have the radius squared, okay? And then we can see that our slope is simply just going to be this pi h. And our y-intercept does not match up with anything, so that means that our y-intercept is simply going to be equal to 0. And so that's the basic idea with these problems, is you're rearranging the equation, matching it up with y equals mx plus b, and figuring out what goes on each axis, what the slope means, what the y-intercept means. So let's try another one, okay? The pressure of a gas is measured as the volume of the container changes. So good old PV equals nRT. In this case, volume is going to be our independent variable. That's the thing that we're manipulating. And pressure is going to be our dependent. So I'm going to solve for my dependent variable. So I can say pressure equals nRT over V. Now I'm going to pull out any constants. In this case, that top is a constant, so I'm going to pull that out. I'm going to write it out in front here, nRT. And what's left then is this volume, but it's on the bottom, so it's actually going to be 1 over V. Okay? Now we've pulled out all our constants. We have our dependent variable by itself, and so we can match this up with y equals mx plus b. Pressure matches with the y. 1 over volume matches with the x. nRT is our slope, and our y-intercept, once again, is going to be 0. So in order to get a linear graph, we would graph pressure on the y, 1 over volume on the x, and our slope then should be equal to nRT. So we could use this potentially to calculate R, that universal gas constant, if we knew the number of moles we had and our temperature. Sorry for the chemistry flashback, but that's how we could use that there. We're going to try one more example here. So for this last one, we're not given our equation right off the bat, but we can use some of our kinematic equation. So an object speeds up with a constant acceleration, the distance is varied, and the final speed is measured. So in this case, let's first think about our dependent and independent variables here. So our final speed, that's going to be our dependent variable. That's the thing that we're measuring. And our distance, that's going to be our independent variable. That's the thing that we are physically changing. We have a constant acceleration, and we are going to make the assumption that we're starting from rest. That should have been stated in the problem here. Okay? And so we're going to use our kinematics equation that does not contain time. So there we have it. We're going to say that our initial velocity is 0, so really the equation that we're left with here is Vf squared equals 2a delta x, okay? We currently have our dependent variable isolated here, that Vf squared, and our independent variable here is this distance, delta x, or our displacement, I should say. So we're going to go ahead and just match this up with y equals mx plus b. This one's a little bit different because actually our y variable is what's changing, and that's perfectly okay if we change our y. Okay, that will still work. So if we go ahead and graph Vf squared on our y-axis, our distance or displacement on our x-axis, we will get a linear graph, and our slope in this case will be equal to 2a. Y-intercept, yet again, is 0. All right, so there we have it. One last example with trying to figure out what we would graph to prove a linear, or to turn this into a linear relationship.